Hi everyone. In this video we're going to talk about the Gram-Schmidt process and also the QR factorization. So to motivate these two ideas, let's recall a big problem that we had. If we wanted to do orthogonal projections onto a subspace, what did we require? Well, we needed a subspace, right? But then we needed a basis of W. Had to be an orthogonal basis. So we needed the basis to be a set of vectors that are pairwise orthogonal. All right, so how in the world, given a basis that wanders up to you on the street, can we convert this basis, any basis, into an orthogonal basis so that we can actually do orthogonal projections? Okay, so this is our motivating question for what we'll call the Gram-Schmidt procedure. Question. Given a basis of vectors v1 up through vn for a subspace W, how can we find, or construct really, how can we construct another basis of vectors that we'll call W1 through Wn, W, for the subspace W, such that the dot product of each of the pairs of W's is 0 whenever I is not equal to j. So the dot product of distinct basis vectors will be 0, ensuring orthogonality, right? So how can we do this? And if we can do this, then we can, our definition of orthogonal projections will work for any subspace. We'll just need to find a basis and then convert it to an orthogonal basis using whatever algorithm that we're about to develop. Yeah. All right, so let's show this with an example. Okay. So let's let W be equal to the span of two vectors v1 and v2. And let's suppose that v1 is the vector 3, 6, 0, and v2 is the vector 1, 2, 2. Yeah? So these two vectors are clearly linearly independent. By definition, they span W. So we certainly know that the set of vectors v1 and v2 form a basis of W. Yeah? But they're clearly also not they're not orthogonal, because the dot product v1 dot v2 is not 0. So it's not an orthogonal basis. So let's see how we can fix it. Let's suppose that v1 maybe looks something like this vector. Who knows? I don't care. Yeah, just a picture. So here's what v1 might look like, and here's what our vector v2 might look like. What we really want is a vector. Let's maybe keep v1, and all that we need is a vector perpendicular to v1 that lies in the subspace W. So let's think really hard. How have we been able to construct vectors perpendicular to a given vector? Orthogonal projections, right? And we know how to orthogonally project onto just the vector v1, right? So let's think about this. Let's form a new basis, and let's let our first basis vector, W1, be equal to the vector v1. So we're going to create a new basis by first letting the first vector in the basis be equal to the v1. And it doesn't matter which one's v1 or v2. Well, let's just pick one. How are we going to construct a vector perpendicular to W1? Well, we know that the vector v2 is equal to the projection of v2 onto the vector v1 plus, I think we called it v2 perp? I don't know. But the vector that is V1 perp? Yeah, V1 perp. Let's call it V1 perp. So it's the vector, the projection of V2 onto the vector V1, or the subspace spanned by V1, right? Plus some vector perpendicular to V1, the sum of which gives you your vector V2. So let's let W2 equal to this perpendicular vector. So let's let W2 be equal to, what's the perpendicular vector? V2 minus the projection of V2 onto V1. Yeah? And that seems like a reasonable thing to do. Let's see if it does anything for us. Well, what do we know now? We know that V1, W1 and W2 are certainly perpendicular because this guy is perpendicular to V1, right? And V1 is W1. So we know that W1 dot W2 is certainly equal to 0. So we know it's perpendicular. We know that W2 is and W1 are in the same span of V1 and V2, so these two vectors certainly live in W. So that means that they must form a basis. Yeah? So we must have that the set W1 and W2 forms an orthogonal basis. So we know right now that W1 and W2 forms an orthogonal basis. For the subspace W, which we defined as the span of the two vectors 3, 6, 0 and 1, 2, 2. Yeah? So let's construct these vectors W and actually write down a basis. I know that W1 will equal to the vector 3, 6, 0, and W2 will equal to the vector V2 1, 2, 2 minus the projection of this vector onto that vector. So we're going to remove all of the information that we've already declared with this W1 vector. So it's going to be 1, 2, 2 minus, well, how do we compute this projection? The dot product here is going to be, let's see, 3 plus 12 looks like 15, divided by the magnitude of this first vector, which is 36 plus 9 is 45, times this vector, and we're just computing this projection. Yeah? Which means that W, oops, and this is, I don't know why I wrote this twice. Sorry about that. So it's just the vector 1, 2, 2, and this is our V2 minus, and this vector over here is the projection of V1 onto V2. Yeah? Or, sorry, V2 onto V1. And if we compute this now, we should see that W2 is equal to the vector 0, 0, 2. And what do we know now about the set W1, W2? It's an orthogonal basis. And let's verify that the dot product is 0, even though we know mathematically it's true. Just take the dot product, you see that it's 0, it's an orthogonal set. And so this process allows us to construct an orthogonal basis for the subspace W. Yeah. How can we construct an orthonormal basis for this subspace W? How do we construct an orthonormal basis? Well, we have an orthogonal basis. All that we need to do is normalize the vectors now. So an orthonormal basis is the vector W1 divided by its magnitude, and the vector W2 divided by its magnitude. Yeah. Okay. Let's do another example. Suppose that W is now another subspace. Suppose it's the span of the vectors 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. Yeah. And our goal in this example is going to be construct an orthonormal basis for W. Yeah. And again, we clearly see that these three vectors do form a basis for W. They're not linearly dependent. This is a linearly dependent set that clearly spans. So these three vectors, let's call them V1, V2, V3. The set V1, V2, V3 certainly forms a basis for W. But we want to construct an orthonormal basis, which means that the dot product of each of our vectors will be 0, and each of them has length 1. How can we do this? The process is going to be the same for us. The process is the same. We're going to initialize, we're going to create a new set of vectors, W1, W2, W3. W1 will be the first vector that we want. Just pick a vector, doesn't matter. We'll call it V1. Okay? What's W2 going to be? W2 is going to be V2 minus the projection of V2 onto W1. So it's the second vector in the list minus you orthogonally project onto the subspace that's already been determined in our orthogonal basis. So what does this become? Well, V2 is 0, 1, 1, 1 minus the dot product up top looks like 3 divided by the magnitude of this vector squared is 4 times the vector 1, 1, 1, 1. And whenever we do the subtraction, I think that we get, looks like, negative 3/4, 1/4, 1/4, 1/4. Sorry, I got a little crammed down there. Yeah. This is our vector W2. And by construction, we know that W2 and W1 are orthogonal. So now the big question now becomes, how do we construct W3? Let's extend this idea. W3, we're going to start off by picking the next vector in our list, V3, and we want to subtract the orthogonal projection of the vector V3 onto the subspace spanned by what we've already orthogonalized. And because W1 and W2 are orthogonal, we can do an orthogonal projection onto the subspace spanned by W1 and W2. So we're really going to project V3 onto the subspace that's the span of the vectors W1 and W2. And we know how to define this because we have an orthogonal basis for W1, the span of W1 and W2. And just to write this out, W3 will be equal to the vector V3 minus the projection of V3 onto W1 minus the projection of V3 onto W2. And again, we're projecting V3 onto the span of the orthogonal basis, of the subspace spanned by the orthogonal basis that we've already constructed. Whenever you do this computation, you should see that W3 is equal to the vector 0, negative 2/3, 1/3, 1/3, I think. Yeah? But definitely pause the video and make sure that you can do this computation yourself. It's just a bunch of dot products and subtraction. There's not a lot of exciting mathematics here. And how do we now construct an orthonormal basis So we know that the set W1, W2, W3 certainly form an orthogonal basis, right? But how do we construct an orthonormal basis? We take each of the elements of our orthogonal set and we divide by its magnitude. Yeah. And that's kind of exciting. Okay. This gives rise to something called the Gram-Schmidt algorithm. And it's the same. So, what's the Gram-Schmidt process? Let V1 through Vp be a basis for a non-zero subspace, and we'll call it W. And suppose this lives in Rn. Okay, so we have a non-zero subspace W. It has some non-zero basis factors for sure. Let's construct our set of W's. We know that W1 we always initialize to be whatever the first vector in our basis is. We'll call it V1. W2 will be equal to V2, the second vector in our list, in our basis list, minus the projection of V2 onto the span. We'll write it really carefully here. Span of V1. It's the same as the span of, or the projection of V2 onto V1 itself, but this is certainly true. W3 is equal to V3 minus the projection of V3 onto the span of, oops, and this should be W1, I guess. I'll keep that as W1, even though they're the same. W1 and W2. And why are we using W's here now? Because I know that W1, W2 will form an orthogonal basis for this subspace. It's true that it will be the same as the span of V1 and V2, but we don't have a good way to define that orthogonal projection onto a subspace if we don't have an orthogonal basis. So we do V3 minus the projection of V3 onto the span of the onto the subspace spanned by the orthogonal basis that we've already constructed. In general, WP is equal to VP minus the projection of VP, it gets a little nasty to write this, I guess, onto the subspace spanned by the P minus 1 orthogonal vectors that we've now constructed. Yeah? And that's not so bad. Whenever we do this, what must we have? We must have that the set W1 through WP is an orthogonal basis and we must have an orthonormal basis is given by W1 divided by its magnitude all the way down to WP divided by its magnitude. And this is the Gram-Schmidt procedure. Let's talk briefly, why do we know that this is always a basis? Let's remember, why is this a basis? I know it's an orthogonal set by construction. I have an orthogonal set of P vectors. They must necessarily be linearly independent, therefore, right? None of them they're all non-zero. And I have the dimension of my subspace is P, so it must form a basis. So it's an orthogonal set, it must form a basis, therefore it must be an orthogonal basis. Yeah? All right. So, let us talk about another problem. Example. Let's let A be equal to the matrix 1, 1, 1, 1, and you say, oh no, this looks familiar. 0, 1, 1, 1, 0, 0, 1, 1. And these are the columns of this matrix are exactly the same vectors that we've already dealt with. Yeah? And in the last example, whenever you compute your orthonormal basis, in this case, for this matrix A, it's going to be an orthonormal basis for the column space of A. If you actually compute the basis, the orthonormal basis, it should be the set 1 half, 1 half, 1 half, 1 half. So be sure to do the computations and check your work here. Negative 3 over square root of 12, 1 over square root of 12, 1 over square root 12, 1 over square root 12. Ooh, it's a big vector. Sorry. Comma. 0. Negative 2 over root 6. 1 over root 6. 1 over root 6. So here is an orthonormal basis for the column space of this matrix now. Yeah? Let's do something fun. Let's construct a new matrix called Q. And into Q, I'm going to throw these three vectors, which we know are an orthonormal basis for the column space of A. And what do we know, as I write this down, what do we know about matrices with orthonormal columns? They're called orthogonal matrices, right? Orthogonal matrices have really nice properties. Here's my matrix. I'll call it Q. What do we know about Q because it has orthonormal vectors? We know that Q transpose times Q must be the identity matrix. Yeah? So let's do something fun. So I hope that you've written this down. Write your Q down. And now what I really want you to compute the matrix Q transpose times A. So pause the video, compute this for yourself. It's really interesting to see it the first time. So the matrix Q transpose times A, I think, is the matrix 2, 0, 0, 3 halves, root 3 over 2, 0, 1, 1 over root 3, and then the square root of 2/3. Yeah. What do we notice about this matrix? We notice that this matrix is upper triangular, and it has positive elements on its diagonal. And this is not an accident. Typically, we call this matrix R. If R is equal to Q transpose times A, how can we solve for the matrix A? In this equation here, multiply on the left on both sides by Q. We write that A is equal to Q times R. So in this equation here, we're going to call this matrix R, and we constructed it by taking Q transpose and multiplying it by A. So we can solve for A again by multiplying both sides by Q transpose, or sorry, by Q, and we know that Q times Q transpose, Q times Q transpose has to be the identity matrix. Yeah? So, this is called the QR factorization. Of a matrix A. Yeah? It's called the QR factorization. What is the QR factorization? Q has columns, or to have a QR factorization, let's let A be an m by n matrix with linearly independent columns. So suppose we start with a matrix with linearly independent columns. Then what we do to find Q is we Gram-Schmidt the columns of A. Yeah? So Q has columns. W1 through Wn. Yeah? So this is our matrix Q. And we know that Q, because we Gram-Schmidt the columns of A, and we started with a linearly independent set, we know that Q transpose times Q has to be equal to the identity matrix. And then R, we construct with Q transpose times A. And this is the QR factorization. What always happens, R is always upper triangular with positive entries on the diagonal. And that always happens. And I think you'll prove this in your homework, yeah? But R will always be an upper triangular matrix, and you'll always have positive diagonal entries. All right. But I know what you're thinking. Who cares, right? Who cares about the QR factorization? Well, the least squares cares, apparently. So one reason that we care is for the least squares. Because it makes, if we have a QR factorization, it makes solving the least squares problem nice and easy. Let's see how. If we know, if we have a QR factorization, A is equal to Q times R, then what do we know is the solution to the least squares problem? We know that we need to construct that normal equation. A transpose A times X equals A transpose B, right? The set of all X's is the solution set for the least squares problem, as we recall. Well, if A is equal to QR, let's plug that into this equation. We get that R transpose Q transpose, because the order swaps whenever you distribute transpose, times QR X is equal to R transpose Q transpose times B. And what happens now? We know that Q transpose times Q is the identity matrix. And so we're left with R transpose times Rx equals to R transpose times Q transpose times B. What do I know about R now? R transpose is lower triangular now, and it has positive diagonal entries, as long as A had linearly independent columns, right? So suppose we have linearly independent columns, so that we can get this QR factorization. If R transpose has positive entries, then it's invertible, because it's lower diagonal with positive entries. It has to be invertible. So that means that we can multiply both sides on the left by R transpose inverse to get Rx equals to Q transpose times B. And this is super nice computationally speaking, because it makes solving, if you have very, very large systems, sets of data that you want to fit a curve to, very, very large sets, this makes solving it a lot easier if you have an upper triangular matrix as your coefficient matrix, because all that we need to do now is back substitution. Yeah. Let's talk briefly about another reason that people care. And this is something called the QR algorithm, which we won't go into, but I just want you to know that it exists because it's super cool. So it's nice to know that this is a thing. People care about eigenvalues and eigenvectors, but how do you find them? We know that eigenvalues are found by constructing a characteristic polynomial and finding its roots. But if we have, say, a 1 million by 1 million matrix or something, then your characteristic polynomial can have up to 1 million roots. And this could be a 1 million degree polynomial. How are you going to solve that? How do you solve it? Turns out this is a computationally very hard problem whenever the degree of the polynomials gets very, very large. Or even moderately large, it becomes non-trivial. So there's something called the QR algorithm to find eigenvalues and eigenvectors, apparently. Turns out. The algorithm goes as follows. A naught initializes to the original matrix A. And then for k equals 1, 2, blah, 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 until your error is good enough, right? So we have a nice for loop going. What we want to do in each step is compute the QR factorization of the matrix A sub k minus 1, and we compute the QR factorization as q sub k minus 1 times r sub k minus 1. And then we let the next matrix in our step be A sub k equals to r, we swap the order, r sub k minus 1 times q sub k minus 1. Yeah? And in the context here for eigenvalues and eigenvectors, we naturally have square matrices, so we don't have any issue with swapping the order here. So A sub k, the next step is going to be swap the order of r and q. To get the next matrix, compute the QR factorization of this product, swap the order, and you keep going. It turns out, if you do this, that the AKs converge to a matrix D with eigenvalues on the diagonal. And then the product, this one's weird, the product q sub k minus 1, all the way down to q sub 0, converges to a matrix with the eigenvectors. So it's kind of cool, and this is a nice way to compute eigenvalues and eigenvectors for a large class of matrices. All right, guys, so I hope that this helps. We've talked about in this video the Schmidt algorithm as well as the QR factorization. We talked a little bit about who cares about both. If you have any questions about this, feel free to reach out via email, or we can set up a time to Zoom to answer any questions that you have. And I thank you so much for watching.